Welcome to Breadboarding. In the previous two videos we've covered an introduction to programmable logic devices and have also gone through all the documentation available on the CUPL programming language which is used to program these chips. The first video we covered the ATF22V10, which is probably the most easy to use chip and is the one I've used most in the Breadboard PC project. And then the previous video we showed the ATF16V8, which although it's smaller, it's a little more complicated due to a number of modes it supports. So this is the third part of the Programmable Logic mini-series in Breadboarding Labs. In this video I'm going to be going through the WinCUPL examples that are provided with WinCUPL and also look at more complex PLD rules. Now if we have a look at the examples that ship with WinCUPL, so this was one of the documents I referred to in the previous video. There are about 41 examples here. However, there is only one example for the 22V10, which is the main one I've been using, and there's a few others for the 16V8, and I think the G20V8 is halfway between the 16 and the 22. So in the previous video I covered the registers and extensions from the dev help PDF, and the key thing here is that when we're looking at documentation, the extensions are one of the cleverer bits of PLDs. However, it can be quite confusing to actually get to grips with these, and the issue here really is that the 16V8 and the 22V10 only use the .d and the .oe for the 16V8, and the asynchronous reset and the synchronous preset are also used with the 22V10. A lot of the other examples use all sorts of more exotic extensions, which can be quite confusing when you're trying to learn how to use PLDs. So what I've done is I've got a list of the relevant samples examples here. So I've gone through the list. There's about 40 odd examples, but these are the only ones really relevant to the sort of devices that we're using. So you'll see the G16V8, the G22V10. In fact, there was only one for the DIP version of this. This one here is in fact the PLCC version. So in fact, there's only one example. It's the reason why I use barrel 22, in that this is the only one that's dedicated to that particular chip that I've been using. But you'll see that the count 10 and gates, so the gates I used, I took this version, I converted it to run on the G22V10. We've also got IODECODE, a lookup and things. So I'm going to go through these, and there's actually specific things in each one. So the adder has an example of functions with parameters. We're going to be looking at the barrel, which is showing fields and array assignments with registers as well. Count 10 has the state machine. So a state machine I haven't really used very much, so I can't say I'm an expert on this in any way, but it does introduce perhaps a simpler way of handling complex scenarios. So this one here, gates, we've already handled in the previous video. The IO decoder makes use of fields and address ranges, and certainly is probably a neater way of handling address decoding than what I've done in the Breadboard PC. It also includes the negative pin definitions as well. Lookup actually includes a table and will allow a conversion from a circle radius to circumference. So it's just showing us sort of a very simple lookup table between one set of numbers and another. And then the TTL one makes use of a macro for 74LS gate, so it has fairly limited examples here. However, there's a separate macro which I'll look at, which actually has many more complex 74LS gates. So probably the best part of 30 odd chips actually have macros that can be used to replace the equivalent 7.4 version. So we'll look at ADDER.PLD first. So this is actually, if we look at the output file produced by this, it's probably easier to see what it's actually doing. So I've already compiled all of these previously. So what you can see here, it takes a 4-bit number X, a 4-bit number Y, adds them together to make Z, and then there's carry output and intermediate carry terms as well used as part of the calculation for this. What we can see here is we've got assigning multiple pins to X1 to X4, multiple pins to Y1 to Y4. So this syntax certainly makes life a lot easier if you're dealing with D0 to D7, for example. You can see we're identifying pin 19 as an output for carry. And then this function here defines our X, Y, carry in and carry out, and we'll actually do the derivations of these on that basis. And then the output Z1, Z2, Z3 and Z4 is then actually just worked out using this. So this is actually providing a sort of a 4-bit adder to take two 4-bit numbers and add them together. So that one. So barrel 22 is probably the most useful one. This is the one I use all the time for getting my projects to compile. So I open this one and then add the other files to the project. So again, if we have a look at the output file for this, the doc file for it, and we have a look at the end. So you can see here that what we've got is D0 to D7, we have a clock, and then we have an S0, S1, S2, and then output enable and preset. So those are all of the pins that we've got here. Basically what this will do is we'll take the number in S0 to S2 and we'll rotate these bits by the number in here. So if it was 0, it would rotate 0 times. If it was 7, it would rotate these bits 7 times using the clock to actually trigger that. And if you want to, we could also then preset the values as well. So what this example shows is using registers. So pin 1 is the clock. We can tell that because this is a G22V10, then it will choose the registered mode because we're going to make reference to registers. We can see that we've defined our S2 to S0 as these pins here. So you don't have to have the pins in sort of continuous ranges. If you use the dot dot notation, that's 2 to 9, but you can actually have sort of discontinuous pins if you want to there. Output enable is pin 13, although we tend to use OE for output enable in most of them. And then the outputs, we can see here that we've got Q7 to 0, and then we've got a couple of fields here. So this field is defined as S0 to S2, input is D0 to D7, and output is Q0 to Q7. And using things in fields like this makes it much easier to manipulate multiple bit data. Now this is probably the most complex bit. It isn't entirely obvious exactly what's going on, but what this basically says is if the shift value is 0, then we want to make the output of the D register for D0, D1, D2, D3, D4, D7 equal to this mapping. Whereas if you've got shift 1, then you'll see that all these are actually shifted, rotated by 1. And when we get down to 7, you'll see that in fact they've all been rotated by 7. So what this is effectively doing is saying map to all of the Q0 to Q7 these values based on if shift is equal to 0 to 7. So by doing this, it actually makes the assignment of this very much easier. You can then see that all of the outputs are then set to this preset, and the output enable is also set to this. The asynchronous reset is just set to 0, so that effectively disables it. Now the thing that is confusing here when you're looking at this in an example is that this doesn't really indicate that in fact what we're actually referring to here is Q0.D, Q1.D, Q2.D, and when we actually look at the documentation file, you won't actually see output there. You'll only really see the Q0 to Q7, the .D. So if we go to the documentation file there, we can now actually see the way how these terms. So you see here that Q0.D is actually now had the output combined with the S0, S1 and S2 terms and the corresponding value that it comes from. So when it's 0, you get D0. When it's 7, we get D7, all the other combinations. You'll see that all these other terms for asynchronous reset, output enable and preset have also been set. If we tried to actually set preset to different values for different Q values, we'd find that it would actually tell us we can't. We can only have one preset term for the AR and the SP with this particular chip. And you can see that all these other ones have then been evaluated like this. So to actually write these down like this is probably a lot more long-winded than it would otherwise be. And you can see also that the S0 output enable is defined as 0, and what that basically means is it's normally an output pin. So these are normally outputs here, the 10 of them, but in fact in this particular case S0 is being used as an input to combine with these other two here. So this is the way how you can tell whether or not something is defined as an input, in that it will have the output enable term hard coded to 0. This symbol table is what I've mentioned in the previous video, that if you have a look in here and if you see anything that hasn't got a pin assigned to it, that indicates there might be an issue. However, obviously where we've got these fields here, then they won't necessarily have a pin assigned to them because they're used to collectively combine pins together. And you can also see here that there's the maximum product terms and your used product terms here. If this number turns out to be bigger than that number, you'll get an error. And you can see that because the different pins have a different number of terms, by moving the pin assignment to the different positions within the chip, then you can actually work around problems if you run out of terms for a particular pin. So this one is probably the most useful from the point of view of the ATF22V10. However, because of the clever syntax that it's using here, going from output.d to knowing that what that is effectively doing is Q0.d, Q1.d, Q2.d is quite a step. And so when learning how to use these, you really need some simpler examples to actually base this on. It's all very clever, showing all of the capabilities, but doesn't make it very easy for actually learning how these things work. So then the count 10. This is using state machine, so I'm not going to go into this in great detail, but just show what this actually uses. There are various versions of the count 10. Some are for later versions of the chips, but the count 10 is the one we want here. You'll see here this is for the G16V8. Again, you'll see here that pin 1 is the clock, pin 11 is the output enable with the negative logic. So this means when OE is low, then output will be enabled. We've got the counter outputs. We've got some definitions for the values of 1 through till 9 here. Then we've got a field which combines both the clear and the direction inputs. So we've got clear and direction, effectively pin 2 and pin 3. And the mode basically then evaluates into up is when we've got no clear and we've got direction 0. Down is clear 0, direction is 1, and then when we have either 2 or 3, then that just means clear. Sequence gives us our state machine. So based on the field count, it will then actually tell us that if we're currently on S0, if up, then the next one state will be S1. If it's down, S9. If it's clear, it goes to S0. And if down, we also set carry. So if you're going down from 0, then we actually set carry. And again, you can see these all go all the way down to this one here. So this is a completely different way of representing this. But if we then look at the output this generates, so if you look at the pins down the bottom, so we've got clock, clear and direction, output enable, and then we've got our outputs Q0 to Q3. But when we look at the way how these expanded product terms, we can see that what that state machine done is actually evaluated that Q0 D register has got all these inputs, Q1 of these, so this has basically implemented all that logic and it's actually consolidated in this way. So again, it's probably a much more sophisticated way of representing certain complicated problems, but it isn't necessarily the easiest way to learn how to use these PLDs. So I would say this is more of an advanced example. Now gates is just the one that we looked at previously. I just converted it to run on the G22V10, just changing the pins. So IO decode is quite an interesting one and is different from the way how I've done IO decoding. I'll show some of those in a few minutes. So this provides sort of chip select signals for input-output functions, and you'll see here that we've actually got address lines A2 to A9, so I guess A0 and A1 probably aren't decoded just because we've got perhaps 4 addresses for each of these chip selects. we've got the memory write signal, which is active low, IO write active low, and then we've got some other inputs to say whether we've got onboard memory access and various other things. Then we've got our various outputs, so the parallel port, real-time clock, serial port 1, serial port 2, and the transceiver. So this is the bidirectional buffer output here. But you'll see, because all of these are active low, and quite often chipsets are active low, because they have the exclamation marks here, we only ever have to worry about whether or not write buffer is true or not. We don't have to worry about inverting it to make it active low. Now you'll see here that the way how these ports are defined, so if you look at the parallel port, the output parallel port is defined as parallel port equation, and the parallel port equation says take the IO address field and evaluate it for 1F4 to 1F7. And on the PC, a lot of the IO ports are in these sorts of ranges, and what this will actually do is then decode this into the corresponding A2 to A9 values that you actually would need to select that particular address range. So this is a neater way of actually defining what your address is, and then it will actually evaluate this into the various true and falses for the A2 to A9 signals. So again, if we look at the document file for this, so you can see if we look at the parallel port output pin has got these rules for the address signals, and you can see the equation is actually in fact the same as well. And when we look at the symbol table here, you can see that a lot of these inputs and outputs are active low, so they have the polarity showing as active low. And again, you can see here the IO address is a field, so it won't necessarily have a pin assigned, because what that is doing is aggregating A2 to A9 as a field. But you can see that this is perhaps a neater way of doing address decoding, certainly neater than what I've done in the breadboard PC so far. Lookup, just quickly look at that. So this is just showing how you can actually define mappings. So what we're saying here is if we've got a diameter of 2 of something, 2 millimeters, 2 inches, then the perimeter will be 13 and going all the way up to 39. And so by defining in the outputs here, if we look at the generated output here, now in fact the chip diagram here is a bit of a mess. The compiler hasn't actually done a very good job of this. So what we've got is some inputs for the radius up to, I think, 5 bits, or 6 bits in fact. And then we've got the outputs, which is the perimeter or the circumference of the circle. So we've got a P0 going all out here. Now in fact, I think you probably could do this using commas and things with a single term if you wanted to. And all this basically is doing is saying there's a table where the radius goes to the perimeter, and what that actually does then is evaluates all these values here. So there's some clever ways of actually combining data and outputting them, but to be honest, for most of the situations I've been involved with, I haven't needed to do this. But the problem really here is that a lot of these examples are a bit too clever for me to actually work out how to use these, and I'll certainly include some simple examples that I've used in the 6809 project, NanoComp project, and the breadboard PC. And the final one here is the TTL one. Now there's 2 lots of macros for TTL. This is actually just showing how to represent some simple TTL gates using macros. So this TTL.PLD basically just defines input A, input B, input C, input D, E and F, then defines 2 outputs, and then what it's doing is actually saying we're going to use a 74LS 7400, which I think is a NAND gate, and it's actually saying that the 2 inputs are input A, input B, and the output is intermediate 1, and then input C and input D and intermediate 2, and then those 2 intermediate outputs then actually been output into the 74LS02. So intermediate output 1 and intermediate output 2 then is going to output 22, and then you can see the 7454 is then actually taking the input B, input C, D and E, and then outputting to 1. So if you have a look at the include of the macro file here that defines this, so you'll see that when you call a macro, you provide the parameters of the pins or the terms that you've got in here, and then it will substitute that in the output. So the TTL.M. So you can see here that we've got the 74LS7400, which is a NAND gate. So P1, P2 are inputs, P3 is the output. It is the AND of P1 and P2 inverted is equal to P3. So you can see this is a quad NAND gate. Then a NOR gate, hex inverters, positive AND gate. I think the 5454 is a 4 wide AND or invert gate. So again, it's showing that we can actually reproduce a lot of the 74LS sort of TTL logic using these PLDs. However, there will be one or two areas where this one here, for example, we can't use with the current chips we're using because it requires a separate clock term for each of the flip-flops. If we can get the ATF750C working, then this one actually should work. So 7474 wouldn't work with the current chips because we don't have the clock terms that we need to specify at a flip-flop level. So the output of this is quite a lot simpler. So you'll see here that effectively the intermediate terms will not have any pin mappings, and the output 2.1 and output 2.2 don't have the intermediate terms. These values have been effectively included in here. And when we look at the pin symbol table here, you can see that the two intermediate terms in fact don't have a pin assigned. Now in this particular case, that is by design, and their intermediate terms being fed from one gate into the next. But obviously if you had a lowercase I rather than both uppercase, then you might end up actually with an extra item in there, and that would indicate that you perhaps made a mistake. Now there is one other set of macros which is worthwhile mentioning. There are two here. The most interesting one is this one of, I think there's about 21 TTL gates here. So this actually shows the 7442 sort of BCD to decimal decoder. We've got various adders, 3 to 8 decoder, 2 times 4 line decoders. So there's a lot of the chips here that you might otherwise have to go out and buy, and if you've got spare PLDs, you may very well find that certainly with the 16V8s, you could probably it will actually be the same sort of price. They're about 90 pence each for the 16V8s, which is probably comparable to some of these chips. And certainly if you've run out of them or you're waiting for them, it's a useful sort of temporary measure. So you can see here we've got various sort of shift registers and things. Now the only issue here is one or two of these ones that will require, so for example something that requires a T register would only work on the ATF750 and higher. It won't work on our other ones, so not all of these macros will work with the current chips that I'm looking at, but once we've got the 750s then these ones should work. And in fact I did spot in here is actually one of my favourite chips, the one that I've actually used in a number of the projects, the 74646, which is kind of like a bi-directional buffer with latches. And you'll see here that this actually implements this in total and has multiple clocks. So we have clock A and clock B. This one's going to be quite interesting once I get the ATF 750s to see if I can actually reproduce this. So that really would be quite interesting to try that out. So that's most of the examples that are relevant to the two chips that we've been looking at. What I was going to do now is to just go through one of the address decoders that I've done on the breadboard PC and look at how to change that with some of the best practice that I've just been showing you. And then we'll also have a look at the CGA Logic 3, which is one of the more complex PLDs with counters and fields and lots of complex conditions. We'll have a look at that. And obviously this is the example macro with the 24LS TTL examples that we've just been looking at. So this is version 5 of the PC Address Decoder. This is the main address decoder that does things like the ROM and the video RAM and various ports and things like that. And you'll see here that all of these outputs are generally active low, so chip enables are generally active low. We've got address 12 to address 19 as inputs, the IO read, IO write, and various other sort of control signals and things coming in here. So you see here, I've defined this in the sort of long-handed way, pin 1 to pin 8 being addressed to A12 to A19. And then when we're actually defining the rules here, all I've been doing is doing the chip enables using sort of hard-coded rules here. So generally, if an address line is true, then it will have just it straight there. If you've got an address line with a not on it, then it basically means that will be 0 for the conditions that we're dealing with here. And because we've defined the enables here as active low, we only ever have to worry about dealing with true positive outcomes from these things here. And when I was first doing this in the early stages, I would actually put the invert on the outside here, and that certainly is a more complicated way of doing things. So you can see that this is certainly a valid way of doing things, and from an understanding everything, this is probably an easier way to understand it. What I've done here is I have gone through and actually adopted the best practice that I've just been showing you. And the main areas here are, rather than having 8 lines for our address pins, I've defined them as pin 1 to 8 being A19 to A12, so that obviously saves us a bit of time doing that. And then all of these chip enables are all defined in the same way, but what I've done is defined a field here called address, which is A19 to A12. And what it's allowed me to do then is to define the chip enables for the various pins there as actually a proper address. So this is kind of a 20-bit address. The thing I didn't realise at the time when I was doing this is that in fact, even though we haven't got bits 11 down to 0, it will actually still work with the top address bits there, and you can still use the full address here. It knows that because we're going from 19 down to 12, it can ignore 11 to 0, so that was something I didn't realise. So we've got some ranges here. So the upper area of RAM, so the bottom area of RAM is just selected on the A19 address line being 0, but this is sort of the, if we wanted more than 512k RAM, we've got our monochrome display adapter video RAM, CGA video RAM in these addresses, and then the ROM is at the top of the memory map there, the top 32k in fact there. And then for the IO ports here, these are just defined as a specific address, just because we're not using the other address line, so it doesn't really matter for those. And then the assignments of these equations to here is much simpler. I guess we could have actually assigned the address directly to the enable here, but I was just reproducing the way how the examples did them. And then if we have a look at the output document files, so you can see that CGA RAM, for example, has those settings there. If we have a look at the output of the best practice, you can see that it's almost identical. The only difference is we've got the equations in there as well. And if you actually look at WinMerge to actually compare these, then in fact, apart from obviously difference in the titles here, you can see here that other than the fact that we've got the address there, the CGA RAM is the same. The only difference with the COM0 is that the IO read and IO write are different order, which is not important. And again, the IO A19 to A12, it just tells us that all those top address lines are 0 when we're doing the IO ports. And you can see there, again, the only difference is that the IO read and IO write is the wrong way around. So it certainly is a better way of actually defining things, and is probably more understandable when you're looking at this to see what the actual address is, and that you don't have to get into all of the complexities of knotting and anding all the addresses together. So then look at CGA Logic 3. So I tend to put the pin map at the top here, so it just makes it a bit easier to make sure you don't get things confused. What we actually have here is an input clock and a number of other inputs coming from another PLD here. we actually have the register values here are actually split between the CQ0 to CQ3. The reason why they're split like this is because some of these terms in the middle had so many intermediate terms that they couldn't fit it in this way. And in addition to having the input pin definitions with some of the polarity set there for active low for the CGA RAM chip select and the memory read chips enable signals. And what this makes use of is two fields, one for the CGA cycle where we're having to worry about which cycle a particular memory operation actually accessed the video RAM, and also this other cycle here which is the dot clock cycle. And you can see that I've got the asynchronous reset here and they're all set to the same thing, so that's fine. But if you try to set these to different values, then you'd find it would actually complain. So this bit here shows the standard conditions needed for a 4-bit counter, and I didn't show it to you previously, but if we look at the counters mac, so this is actually a macro for 10-bit counter, and I think there's a 11-bit counter as well, 11-bit counter. So you'll see that if you've got a counter going Q0 to Q9, that the way how the terms actually need to be combined to actually build a counter like this is not particularly trivial, and obviously this macro here actually provides certainly the value. So if you just needed to do a 4-bit counter, then in fact if you just copied these bits here, that would actually give you the 4 bits that you actually would need. If you needed a 7-bit or 8-bit counter, this will give you all the terms you actually need. So it's worthwhile knowing about that counters.mac. And then what we've got here is where we've got the video RAM write enable, what you can see is we're able to actually combine when the CQ cycle value 4 and our dot clock cycle value 5 and our add clock value or, and they've got a really complicated sort of set of conditions here. And similarly for the address output enable, we've got a sort of a slightly different version. And you can see we've also got various graphics modes and things in here as well. And this produces a document file here, and you can see that the conditions in here are really quite complicated, and if you were trying to work out that by hand it would be really quite challenging. And when we actually look at the pin table here, you can see that in some cases here we have max P term 16 and 13 there. And I didn't, certainly at an earlier stage in the project, I'd simplified the rules at a certain point. I certainly had 16 and 16 there. So this just shows that using the fields in particular is a very sort of good way of actually hiding complexity and getting all of these various terms in here. Each one of these is effectively an input to an OR gate in the PLD. So that's what it's going to do in this video. In the next video, I'm planning to go into how PLDs really work. So this is really looking at the fuses and terms, actually taking one of the simplest PLDs you can get with just perhaps a single pin mapped to one output pin, and actually look at how that's represented in the JED file, and also take a look at the JDEC file standard itself as well. And we're also going to be looking at the more advanced DIP chip, the ATF750C. So I'm pleased to say that the chips arrived actually yesterday, and I've also been able to verify that in fact that my T56 programmer does actually program the ATF750Cs. I'm still getting problems with the ATF2500C, which I'm still looking into. So if you see here, this is the T56 programmer, which was the more expensive version. Certainly when I bought it during the chip shortage, it was probably more expensive than it is now. I believe there is a new version, something like a T76, I think, which is being advertised now. I haven't seen anywhere on Amazon where you can get this. And if we just have a quick look at this, you can hopefully just be able to see this is that Atmel ATF750C 10PU. So that's what I'm going to be looking at in the next video, and this should really allow us to do some much more interesting things with the PLDs. One of the things I'm going to be looking at is whether I can replace some of the Intel controller chips, such as the clock controller and the bus controller, see whether such a chip like this could actually replace those. So if you don't want to miss out on future videos, please hit subscribe, and if you found the content interesting, please hit like. It just helps to make the videos available to more people on YouTube. Thanks for watching.